Okay guys, so I'm going to do a video on the reactions of alcohols. I think all the other aspects of alcohols that are covered in the syllabus for AS Chemistry are done on the YouTube website, so you have videos for those already. And some of the other stuff like combustion is really pretty simple, no different than any of the other combustion reactions that you did. So this is to do with section 2.6 of the specification, and I will run through these reactions. I'll run through sort of observations of them, and then I'll write a few equations for sort of very simple alcohols and how to name the products, and then I'll write some maybe slightly more difficult reactions, but they shouldn't be too bad at AS level. You have also got a PowerPoint, or two PowerPoints that I sent you through to cover. One covers sodium reactions on its own, and the other PowerPoint covers reactions of hydrogen bromide and phosphorus pentachloride, PCl. By the way, if I talk about phosphorus pentachloride, that's what I'm referring to there. So we'll walk through these one at a time here, and hopefully you've got some questions also at the back of your notes, your alcohols notes, which cover this. I think pretty much everybody has done this, but there were a few of you who are missing from the last couple of days of class who would have missed out on this. I've also sent you a YouTube video, a very good YouTube video on the next part of alcohols, which leads into infrared spectroscopy. So if you can please make sure and have a look at that and do the questions also. Right, so we'll start with sodium. Okay, now this is a parallel reaction to the reaction of sodium with water that you did at GCSE. If you can sort of remember, maybe your teacher took a bit of sodium, dropped it into water, it did all the usual things that you probably remember. There was effervescence, okay, fizzing, there was a lot of heat given off, the sodium floated on the surface, the sodium slowly-ish disappeared. You may, if there was enough heat produced, have seen in there a yellow flame, and at the final you would have seen a colourless solution. Now the reaction that was happening there was sodium with water give you a colourless solution of soluble sodium hydroxide, and the fizzing was of course from the hydrogen gas that was produced. The yellow flame was from the burning sodium. If the heat gets high enough, that can ignite the hydrogen that's being produced around the sodium, and that gives you the yellow flame. Everything else in there, the floating, is because the sodium is a bit less dense than water. Okay, now if I just finish that off, that's your reaction. Balance that. Okay, so that'll be your reaction. This is a very similar reaction of an alcohol with water. Now the only thing really that is, well, in fact there's a couple of things that are different. Okay, the first thing that is different is that the whole reaction with an alcohol is a bit slower and a bit steadier. You'll notice that with an alcohol the sodium will sink. That's a pretty significant observation. Because it sinks and it's down at the bottom of the ethanol, you will not get this ignition, so there will be no flame. There's not enough energy produced in order for it to form a flame down there. You will get a colourless solution. Sometimes they ask you what happens to that colour solution if you evaporate all of that liquid to dryness. Well, when you do that, you will get white crystals in the same way you would here. Sodium hydroxide, if you evaporate all the water off, sodium hydroxide is a white solid, so you'll get exactly the same. Although obviously a different crystal, a different solid will be produced when you do it with an alcohol, but it's still a group 1 salt, and you get colourless solution going to white crystals if you evaporate all the water off. Okay, you still get heat, you still get fizzing, and the gas is still hydrogen gas. The sodium will still disappear in there. You won't get the yellow flame anymore. You will get a colourless solution at the end, and of course we already covered the fact that it doesn't float. So let's have a look at the sort of the chemistry or the reactions of it and naming these products. The products that you get here are called alk, ox, oxides, and if you know your chemistry now, you know that the term alk or alkyl group is sort of talking about your ethyls and your methyls, etc. So these are things called eth oxides, meth oxides. So look, it's not alkyl oxide. So that's the reason why I'm dropping the YL here, if you like. So there's ethyl oxide, or eth oxide, sorry, meth oxide, etc. Sometimes we need a number on that, sometimes we don't. Okay, we'll have a look at that, but we should be pretty adept at knowing when we need sort of prop 2 oxide, but 2 oxide, etc. We should be on the ball with regards to that. Anyway, okay, so this one clear. Well, no, I'll keep as much of this on here as I possibly can, right? So let's look at the equation. We'll do it just for ethanol with sodium. Okay, and we get C2H5OH Na plus we get half a mole of hydrogen gas produced. That explains the fizzing. Now, where we need to be careful here is because we're and we have it sort of driven into us to remember to, if we're asked to draw all the bonds within the OH group, we draw the bond between the O and the H. We need to make sure that we don't actually do that this time, because now we have an ionic part to this molecule, and that line that we hop on at you to draw there between the O and the H in the ethanol represents the sharing of electrons, or a covalent bond. In other words, this is now an ionic part of the molecule, and that means that we most certainly, if we did draw that line that I've just put in there in the red, that's actually going to cost us marks. Now, this compound that I have here then is called alk oxide. It's particularly, the metal involved is sodium. It's 2 carbons, so it's sodium eth oxide. Okay, relatively easy named. So we now have this sort of covalent section to the molecule and an ionic section to the molecule, and that's quite useful from a chemist's standpoint, because it now gives, this ionic section gives greater solubility. Okay, not that this wasn't soluble already, but this is even more soluble. It also means then, if I did evaporate this to dryness, that this is actually now a white solid. So if I was going to use this to make in drug manufacture, etc., it'd be quite easy to turn this compound into tablets. Indeed, that's exactly what pharmaceuticals do. They incorporate these ionic groups into covalent molecules in order to raise the melting point and turn them into solids, so they can actually package them up as tablets, which are a much more convenient form of pharmaceutical than liquid. And they also, solubility is important within the pharmaceutical industry as well, in order for that tablet or drug to dissolve into water, or to dissolve into bodily tissues. So a couple of things that the examiner might ask you about, as well as obviously the observations, which are always key. Okay, so we'll just have a look at a couple of other equations. I'm going to have to clear the board here now because I'm just getting too tight for space. Okay, so let's say they asked us about propanol plus my sodium. Okay, again, we're always operating around the functional group, guys, so we have O minus, Na plus. Now this time we do need to put a number in, so this is called, again, it's of course sodium. Okay, it is prop. Prop is on number 2, so this is sodium prop 2 oxide, and again we do not have any covalent bonding between the O minus and the Na plus. Charges aren't necessarily having to be there to be present. I just sort of put them in. It's just probably good practice to put them in, but maybe not necessarily. At the end of the day, the positives cancel out the negatives. Okay. So let's take a look at one then, perhaps where we would have 2 OH groups. And again, like I always taught you when you're doing your organic chemistry, okay, you just treat them exactly the same. Okay, now this time we have 2 OH groups, so if one OH group required 1 sodium up there, we're going to need 2 OH groups, are going to require 2 sodiums, and we just treat each of them in exactly the same way. Okay, so remember they're in position 1 and position 2, so we have NaO, plus and minus if you like, and again we have O minus NA there, and this time, sorry, I forgot my hydrogen up here, which would cost me marks if I was asked for a balanced symbol equation. Okay, I have a half a mole of hydrogen produced in this context. I have an entire mole of it produced in this context. Okay, how would I name this? Well, again, it will be just simply sodium. Okay, I have prop. Sorry, it shouldn't be there. Sodium prop. I have a dioxide. Okay, and I have it on numbers 1 and 2 hyphens. Now I have 2 groups this time, so it becomes propa 1,2 dioxide. Okay, so I think that's probably as much as we need to do, and that we've done all the observations. We've written a couple of equations. We've dealt with alcohols with which are diols, and I don't think they'll ask you much more than that. We'll look at PCl5 then. Okay, so PCl5 or phosphorus pentachloride. Right, this is your sort of stock test for an alcohol group, so for an OH group. Okay, now we've done other tests where we have sort of had oxidation, but that will tell us if we have a primary or secondary alcohol. This just gives us a test for any alcohol at all, whether that be primary, whether that be secondary, or whether that be tertiary. Now we'll have a look at the reaction and the equation, and we'll look at the observations that you would expect to get from this reaction, and it's how we then use this to identify the presence of an alcohol group within a colourless liquid. So if we have our alcohol group, we're reacted with PCl5. Of course, that's a white solid, by the way. PCl5, pretty nasty white solid. Always wear gloves when you're using it. Okay, it will react with moisture on your hands to make hydrochloric acid and other nasty stuff that you don't want on your hands. Okay, and we've gone from alcohol group to chloroalkane, so it's a good way to make a chloroalkane. Plus POCl3, that's called phosphorus oxychloride or phosphorus oxytrichloride, depending on the book that you read, on the notes that you go to, plus HCl. Now that is not necessarily hydrochloric acid, that is HCl gas, so when that comes up out of the test tube, and that's one of our main observations. So if I have a colourless liquid, and I'm not sure what it is, and I add PCl5 to it, and I get some steamy fumes, and that's exactly what they are, it just looks like steam rising up out of the test tube. Okay, those steamy fumes are probably HCl, and this is the first sort of indicator that my original compound was an alcohol. Now I can do two things with those fumes. I can test them with damp blue, and it has to be damp, remember. Okay, litmus paper. That will go red. Okay, it doesn't go white. White, remember, is chlorine, so it goes red, and that's probably a pretty good indicator that that gas is indeed HCl, coupled with the fact that it gave me steamy fumes. The better test that I prefer is with conch ammonia, conch NH3, and that gives me a very dense white smoky fumes. Okay, and those are ammonium chloride. Okay, we'll have a look at sort of what that's all about in a wee second, but that's your best test. So if you get positive tests here, steamy fumes, followed up by these tests here, then you're pretty confident that your original substance is, of course, an alcohol. So what you do is take your test tube. Okay, you have your colourless liquid in there. You suspect it's an alcohol, but you're not sure. You take a little spatula, excuse my artwork, okay, of PCl5, and of course you drop it in it, and what you'll get then from that are these steamy fumes. They're not green, by the way, that's just the only colour I had. Okay, and you then take your glass rod, which you had dipped in conch ammonia. Okay, so that's my conch. C means concentrated, by the way, conch ammonia, and then from that, when it makes contact with these, as I've represented them by green, HCl, then I get these very thick white fumes That is of course ammonium chloride, which is just ammonia plus the HCl gives me NH4Cl. Those are my dense white fumes. Okay, so if all of that works out and you're getting positive tests there, then you're pretty confident that your original alcohol isn't, or your original substance, sorry, is indeed an alcohol. It's a very vigorous reaction down here. I suppose I should have said that as well. Get a lot of hissing and fizzing and popping going on down in there. Okay, now we'll do a couple of quick equations for this, but this really isn't very difficult. All you're doing again is, if I took, let's say, C2H5, good old ethanol, plus PCl5, I'm simply getting my chlorinated alkane plus the POCl3 plus of course the HCl. So that's just very easy to name that one. Chloroethane, no number needed. Okay, I'll just take something else, maybe with a couple of OH groups on it. Okay, same ones I took in the last one. Okay, and we have PCl5 again. Now this time remember, we're going to need to double up on our PCl5s because we need one per functional group. And again, I'll just draw it out full structural for you, make life a little bit easier. Okay, each OH group is treated independently. Okay, I remember to double up on those, and I will double up on those. So this time I get 1, 2, hyphen 1, comma 2, hyphen, that's dichloro, and it's 3 carbon compound, all single bonds, dichloropropane. So that's, I think, pretty straightforward. You don't get much more difficult than that in an AS chemistry exam. So if you're able to deal with both of those equations and remember, learn the observations, etc., you should be fine. Right, the third one that we look at is the last substitution reaction of alcohols. And this is with HBr, hydrogen bromide. Oops, sorry, get rid of that. Hydrogen bromide. Now what you do need to be a little bit careful of here is sometimes they don't tell you directly with hydrogen bromide because the reagents, actually the hydrogen bromide is the reactant, but it is made in situ, which means in the place of the reaction. You don't go and lift a bottle of it off the shelf, and it is made by reacting concentrated sulfuric acid with either sodium bromide or potassium bromide. It's the reaction that you used in that rather lengthy preparation of 1-bromobutane that you did with all the reflux and distillation and purification. Now you do need to know the equation for the preparation of the hydrogen bromide, or the and that is where the sulfuric acid reacts with sodium bromide, and you try and keep that pretty cool. If you remember, you did it in ice. Okay, and that gives you sodium, and this is important, sodium hydrogen sulfate, and not sodium sulfate that a lot of people write, so don't write that please, and you get your HBr. So there you go, your HBr is made in situ, in the place of the reaction, and your alcohol is present in there as well. So as soon as the alcohol is present, okay, and the HBr is present, they will react together, and this time, whereas the PCl5 give you a chlorinated alkane, now we get an alkane with bromo on it, okay, presumably called a brominated alkane. Alright, and that leaves me also with water produced. Okay, now you won't be asked about observations in this reaction. There's nothing sort of standard that you actually see here, but you will be asked certainly to maybe write this equation to understand what the term in situ means. Okay, and then of course certainly to write this equation. So we'll just do a couple of could take a couple of alcohols and write them, and again, just like all of these guys, there's questions at the back of the notes to test you on these, and I have all of the answers. I can't remember if I've fireflied you the answers or not, but if not, you want to practice them, you can, if I haven't, you can ask me for them. I know most of you have gone over these in class, but there are a few of you who weren't in class, which is why I'm doing this video. Okay, so again, same as all functional group chemistry, guys, we concentrate our efforts around the functional group. So we've gone from propan-2-ol to 2-bromo-propane, and remember the 2 is of course important, as is the hyphen. Lose the hyphen, lose the marks. Okay, I'll do one more. Not very difficult, as you're probably picking up. Okay, so again, functional group, concentrate our efforts around that. Okay, the methyl group remains unchanged, and OH goes to a BR, and of course we got water, so just be careful naming this one. Remember, the BR is the functional group and will get priority, so therefore my methyl group here has to be at position 3, and my BR group here is of course going to be on position number 2. Okay, I can catch a few people out. So that is of course 2 bromo, 3 methyl, and that's a 4 carbon single bonded chain butane. Okay, right, everyone happy enough with that? And then I'll do one last one. Okay. Now I have 2 OH groups in this one, of course. So if we have 2 OH groups, we will need, hopefully you're cotton onto this by now, 2 HBRs. Okay. And just take our functional group and treat them all exactly the same. Okay, my product then is 1, 2, 3 tri-bromo, and it's a butyl single bonds butane. Okay, commas and hyphens important, need to be in there in order for you to get the marks. Okay, the only reason I did that one is just to make sure that people remember, even though I'm only substituting 2 groups, I already had a BR on there, so therefore I need to remember that I have got 1, 2, 3 tri-bromo-butane. Okay guys, that covers the 3 substitution reactions that some of you were missing in class. You have, as I said, the questions at the back of your notes. There's loads of practice ones, sort of simple ones, tricky ones, and in between ones. And you've also got your textbook as well and the answers to that. Okay, hope that helps, and if you have any queries, feel free to ask.